In this lesson, we'll be reviewing the metric system and how to convert between different metric prefixes. By the end of this lesson, you should be able to identify the key metric units that are used in science and be able to use dimensional analysis to convert between different complex units. Something I'm going to say over and over this semester is to remember your units. A lot of my students in the past have referred to units as labels, which has never quite sat right with me. A label is something you can peel off without changing what's underneath. A unit is not like that. If you remove the unit, the number loses its meaning. So we have some examples. In the first example, Mo has written down the number 5 on a piece of paper. And we're like, 5 what? What is he trying to convey? Is he talking about 5 centimeters, 5 tons, or 5 degrees C? There's a big difference. Not all 5s are going to be the same thing. Another example that may be a little bit more meaningful at this point in the semester is the question, is 50 a lot? Again, it depends on 50 of what. So we have to know what the unit is. So hopefully, one would presume that you would know that 50 cents is a lot less than $50, which is a lot less than $50,000. Notice how I snuck in a little metric prefix there with the K, because K means thousand. All right, so why use the metric system? When my son was in high school, he always hated having to review the metric system. He thought it was stupid. Kind of, hurt my little scientist heart. So let's step back in time to using the imperial or the English system. If you've ever taken a foods class, you might know that 3 teaspoons are 1 tablespoon, 16 tablespoons are a cup, 2 cups are a pint, and 8 pints are a gallon. So if for some reason you wanted to know this, if you wanted to know how many teaspoons there are in a gallon, you would have to do some math. You would say, all right, well, 1 gallon is 8 pints, which is 16 cups. 16 cups is 256 tablespoons, which means that there are 768 teaspoons in 1 gallon. So takeaway message there, you have to do math to figure this out. You got to do a bunch of conversions. On the other hand, if you're looking at volume measurements using the metric system, as long as you know your definitions, you don't have to do any math at all. If you wanted to figure out how many milliliters there are in a liter, you would say, well, milli means 1/1000th. So therefore, there are 1,000 milliliters in 1 liter. No math required. All right, so there was a lot of different ways to do metric conversions. I'm going to show you 2 different ways. The first way is using the mnemonic, King Henry died by drinking chocolate milk. A lot of people use stair steps, some people use ladders. I developed this technique, I call it the metric walk it out. It helped a lot of my early students, and at the time when I was developing this technique, my students would jump out of their chairs and start doing a dance that was very popular at the time called the walk it out. I decided to try to channel some of their energy into something a little bit more useful than bouncing around the room. So hence, metric walk it out. So the key thing for this is you always want to pay attention to your units in this case and how many letters you have in it. So if you have 2 letters, like we have in this first example, so we have, whoops, darn it, it advanced. There. So we have kilograms, so we're going to ignore the grams part and just focus in on the K. So you're going to put your starting decimal point to the right of whatever that first letter is. So to the right of the K. Make sure you got your lefts and your right straight. After that, we're going to fill in the number. So we have 8 kilograms, so we're going to put an 8 in the box. Decimal points go on the lines, and numbers go in the boxes. So now we got our starting number set up. We want to look at where we're trying to get to. That has just 1 letter, so that means we're talking about the base. So we're going to walk the decimal point over and stop when we are to the right of the base unit. There we go. And now the next step would be to fill in the dips with zeros. And so this tells us that there are 8,000 grams and 8 kilograms. Another example. So we're starting out with 18.5 milliliters. So again, we look at the unit, we say, all right, we have two letters, so we're going to focus in on the M. The only time M is used, like over here, is when it's milli. If you're talking about meters, if it just has meters, that would be the base unit. M's are a little confusing. So we're going to put our decimal point to the right of the M, and then we're going to fill in the numbers, one number per box. In the past, I've had students do very peculiar things. They put the decimal point in the right place, but then they write all the numbers after the decimal point. You are reconstructing the number that you're starting out with. So if it's 18.5, you should end up with 18.5 down in the chart. So now we're going to look it over and stop when we are to go to the K. All right. And then now we fill in the dips with zeros. And so there would be 0.0000185 kiloliters in 18.5 milliliters. Something we're going to be looking at or reminding ourselves how to do is how to write numbers in scientific notation. So the general rules for writing stuff in scientific notation is you want to count how many steps you have to move that decimal point over so that there is one number in front of it. So let's do it. So we go. I'll try to do this with my pen. I'm not very good at this. So 1, 2, 3, 4, 5. So we moved our decimal point to the right. So that means that the scientific notation for this would be 185 times 10 to the minus 5 kiloliters. All right, so let's go on to the next. Now I did come up with another mnemonic for larger metric conversions. Mighty King Henry died by drinking chocolate milk Monday, and that includes some of the bigger units, mega. Put it back on pointer. Mega also takes care of some of the smaller units, micro. But the problem is that it leaves out this 10 to the 5th, 10 to the 4th, 10 to the minus 4th, 10 to the minus 5th units, because while they are there, they don't have specific names. So you have to remember to add them in if you make a chart. So let's look at an example. So we're going to convert 10 micrometers to megameters. So we set up our number. So it's 10 point. So 10 point to the right of the mu, which is what that funny looking U is. It's Greek letter. Greek letters are cool. And then we're going to stop our decimal point, walk it over, and stop when we are to the right of the mega. So we go ahead and do that. And if you're doing this on paper, I usually use an X for the second one, just so I can keep track of which one's which. So we go ahead and remove the decimal point over, fill in the dips with zeros. Now that is a silly number of zeros, so we're definitely going to write that one in scientific notation. So that works out to be 1.0 times 10 to the minus 11th megameters. As I said on the previous slide, if you have to move your decimal point to the right when you're writing it in scientific notation, like we do in this case, you're going to end up with a negative exponent. If you move it to the left, you're going to end up with a positive exponent. So let's look at a few more examples as far as that goes. So as I showed you, we want to count the number of steps you have to move the decimal point so there's only one number to the left of the decimal point. That is standard scientific notation. If you write numbers in weird scientific notation where you got more than one number in there, I'm going to mark it wrong. Some of you have calculators where it gets set in engineering mode and it'll have more than one number in front of that decimal point. So make sure your calculators are set appropriately. And then the number of steps are going to be equal to the exponent that goes on the 10. So there are two cases. If the number is bigger than 1, then you end up with a positive exponent. I have trouble with my lefts and my rights, so it's a little bit easier for me to say, well, it's bigger than 1, so therefore I have a positive number of steps. So say, for example, we wanted to convert 101.33 kilopascals into scientific notation. This number is bigger than 1. So we're going to have a positive number of steps. We have to count the steps. So we go 1, 2 steps. So it's going to be plus 2 steps. And we end up with 1.0133 times 10 to the second kilopascals. Again, make sure you only have one number to the left of the decimal point, and that since the number is bigger than 1, we have a positive 2 on there, and that 2 corresponds to the number of steps that we moved it. The other case is, if we have a number that's smaller than 1, you will end up with a negative exponent. So here we have 0.0015 milligrams. So we are going to move it 1, 2, 3. I'm using the mouse again, shouldn't do that. And it's smaller than 1, so it's going to be negative 3 steps. So it's 1.5 times 10 to the minus 3 milligrams. So another classroom rule. So if you have a number that has 2 or more zeros in it, then you must write it in scientific notation. It gets really hard to grade papers when there's people writing things with, 7, 8 zeros in them. And once it's past about 2 zeros, then that's when it starts getting difficult. So again, if you have two or more zeros in your number, and that goes for either end, either in front of the numbers or behind the numbers, then you should be writing your number in scientific notation. So hopefully we will build up our scientific notation writing skills during this semester. And if you have trouble with that, just ask me and I'll show you how to set your calculator so that it will always put your numbers in scientific notation. All right, so the walk it out method works well if you're just doing a very simple, one prefix to another prefix kind of conversion. What if you have a complex unit or a derived unit? In this case, we're going to use something called dimensional analysis. This is also called the factor label method. And this method can be used to solve any kind of conversion problem. And the key to this is to remember that units cancel out just like numbers do in fractions. So you've already seen this. So for example, if we wanted to multiply 3/7 by 2/3, we say, well, I got the same number in the numerator and the denominator, so I can cancel them out, and we will get the answer is 2/7. Now, these numbers are just symbols. They represent quantities of things. So if you see the 2, you know what quantity it's talking about there. 3 would be a different quantity. Units are the same way. They represent specific quantities of things, so therefore they can cancel. So the steps to using dimensional analysis to solve this kind of conversion problem is to write down your starting number and put it over 1. We're going to have a bunch of fraction kind of things, notation, so you want to make sure that everything that's supposed to be in the numerator stays in the numerator. So we're starting out with 1 day, so we're going to write 1 day over 1. The next step would be you're just going to multiply by conversion factors, where you have the unit that is up here in the numerator is going to end up down in the denominator with the next conversion factor, so we can cancel it out. So we're going to work our way from day to seconds. So 1 day, I don't know offhand how many seconds there are in a day, so I'm going to say, but I do know that there are 24 hours in a day. And so now our days have canceled. You say, well, we're still not there. We have 24 hours. We want seconds. So hopefully you know that every hour is 60 minutes. So again, we put the hour down in the denominator so that we can cancel it out. And then we say, well, we're still not quite there. We have minutes and we want seconds. So we need one more conversion factor. So there's 60 seconds in 1 minute. And so now the minutes have canceled. And what you do is you just multiply everything across the top. So 1 times 24 times 60 times 60. And then we're going to divide it by the product of the denominator, which is just 1 in this case. And we get that there are 86,400 seconds in 1 day. And remembering it has more than 2 zeros, or has 2 zeros, so we're going to write that in scientific notation, which is where the 8.64 times 10 to the 4th seconds comes from. All right, so this table is just a reference. It's to show you how to go between the different metric units. I know a lot of people, when they first start doing this, they don't necessarily have them all memorized. The way you read this table is the base units are going to be where you have just one letter. And I have examples over here. So like 1 gram, or 1 times 10 to the 6 grams, a meter, a mole. A mole is a very important unit in chemistry. Don't have anything else that's different. Oh, liters. So that number is going to go in front of the 1 letter if you are trying to do that. And then this is for the prefix plus a unit. So in this case, it says that for every 1 million grams, 1 letter, you have 1 megagram. And now it gets easier to use chart after a bit of practice. Notice we also have nano on here, which is a billionth. 1 nanometer is a billionth of a meter. That one got left off of that King Henry thing. So say we wanted to convert from 7.25 centimeters per second to kilometers per hour. So now we have, I guess you call it, it's a derived unit, but it's a unit above the bar and below the bar. So you just write it down like you did before. So this tells you that you have 7.25 centimeters, right there, for every 1 second. So now we have it over 1. And we're going to convert the time part first because I have that one up there. This is something you would know probably if you were in physics, not necessarily so much for chemistry. And all right, so there's 3,600 seconds in 1 hour. So now our seconds have canceled. And we have hours, which is what we want, so we can stop messing with the denominator part of the unit. Now we want to get rid of centimeters. Now when you use this chart, you always have to go back to the base unit because it gives you the conversions between the different base units. So you say, all right, well, I want to get rid of centimeters, so centimeters are going to go down to the denominator. And I look up here at centi, so for every 1 meter, there's 100 centis. Or so every 1 base, you have 100 cents. Just think cents on a dollar. So now we have gotten rid of centimeters. We're still left with meters. We want kilometers. So we need one more conversion factor. So this is for kilometers. So we see that we have 1,000 meters for every 1 kilometer. So the double unit, 2 letters. So 1,000 meters for every 1 kilometer. It's really important that you have that number with the appropriate thing. I have a lot of people, they always put the number in front of the kilo or in front of the 2-letter unit. So this says 1,000 1 letters, so 1,000 meters for every 1 2-letter. So we have 1 2-letter. All right, so now we have canceled out our meters. We're left with kilometers per hour. Go ahead and multiply all this stuff across the top. So 7.25 times 3,600, and then divide it by the product of 100 and 1,000, so 100,000. And we get that this works out to be 0.261 kilometers per hour. All right, so something a bit silly, and this is actually a bonus question on the worksheet that goes with this lesson. You're supposed to use dimensional analysis in order to solve the following problem. So it gives us a bunch of conversion factors, and then it says what each one of those bullets is. And it says if there are 5 Fruminous Bandersnatches, how many Jabberwocks are there? So I'll get you started on it. So the key to this one is just to make up some units. So right here we have 5 Fruminous Bandersnatches. So I'm going to say a Bandersnatch is going to be, unit is going to be a BS. So our starting number is 5 BS, put it over 1. Now we just want to find conversions between Bandersnatches to something else. And so that's this first one, or this bullet right here. It tells us that in each Tulgey Wood there is 1 Fruminous Bandersnatch. So we want to get rid of Bandersnatches. And that says that we have 1 Tulgey Wood. So now that one, I don't know why I can't draw straight lines, is done. You're going to use each bullet, and you're only going to use it once. And we have gotten rid of Bandersnatches. So now we have Tulgey Wood. So let's find one that has Tulgey Wood. Here we have the first bullet. It says there are 20 tum-tum trees in the Tulgey Wood. So we have 1 Tulgey Wood, and it has 20 tum-tum trees in it. Now Tulgey Wood is canceled out, and we're left with tum-tum trees, and you just keep going until you've used them all up, and you should end up with a whole number of Jabberwocks that's less than 10. Just give you a ballpark figure. All right, SI units. Every 20 years or so, they get together, the people that decide on these things, get together and decide on a common system of units to use. It used to be the CGS unit, which was centimeters, grams, and seconds. And then they decided that those were too small, and then they switched to the MKS system, which is what they're currently using, which means that all of your units have to be based on meters, kilograms, and seconds. And then that way, if you have something like a Newton, you know that it is going to be a certain number of kilograms that are being moved at a certain acceleration. We are not strictly sticking with the MKS system, but I did want to mention that these are often called just SI units, just means standard metric units. So for length, we're going to be, whenever you see meters, the 1-letter unit, not the milli, we're talking about a length. Mass is going to be kilograms. We're actually going to be using grams more often than we use kilograms. Grams. And then we have time would be seconds. We're not going to worry about amps and candelas. Temperature is Kelvin. We also use degrees C. And then mole is an amount of a substance, kind of like a dozen. We'll get to that. So just make sure that you are using metric units when you are doing your calculations. So no inches, no yards, no miles. Never, ever use Fahrenheit. I always call it the F word. We're not using Fahrenheit in here. All right, so to wrap it up, the metric system is all based on powers of 10, which makes it really easy to do conversions because you're just moving the decimal point around. The metric prefixes tell you the size or the scale of a measurement. So kilo tells you it's pretty big. Milli or micro tells you it's pretty small. Dimensional analysis, also called the factor label method, uses units to help guide the conversion process so that you can deliberately work your way towards the final unit. Remember, a classroom rule is that if you have 2 or more zeros, we're going to write our numbers in scientific notation. And also remember, we're always going to include our units, and that units are not labels. They actually convey meaning. They're more than just something that got stuck on it to dress it up a little bit. And then our answers must always include the units, or they are going to be incomplete. Typically, when I'm grading a problem set, it's going to be 2 points for showing your work, 1 point for the correct answer, and 1 point for the unit. So if you just write down a random number, you're not going to get very many points for that one. All right, so that's it on the metric conversions and the metric system. Thanks for listening.